solving rational equations. In this presentation, we're going to talk about solving rational equations. And what we're going to do in this presentation is take a look at rational equations such that we have a fraction equal to a fraction, or what a lot of times is referred to as a proportion. So in doing so, I'd like to just kind of jump right into there and start off by solving some of these examples and going through a common strategy. So when we see that we have a fraction equal to a fraction, we can use that concept of cross multiplication or however you want to reference it. But what we can do is we can actually envision that we're multiplying both sides of the equation by 2x plus 1, and then multiplying both sides of the equation by the x minus 1. So if we would multiply both sides by 2x plus 1, they reduce on this side, and that's why I'm just left with a 5. And then that's why I have 4 times 2x plus 1 here. Flip the script, when I multiply both sides by x minus 1, they reduce here, and that's why I just multiply by the 5. That's what enables us or permits us to go ahead and do the cross multiplication. Now from here, we're in a good place because we no longer have a rational equation, we just have a linear algebraic equation. So in solving it, we would just distribute respectively on both sides. I'm going to subtract 5x, then I'll subtract 4, and I get x equals negative 3. So whenever I'm doing these types of problems here, what I want to be able to do is I want to make sure that I can take my rational equation and try to get into our comfort zone. And in this case, I was able to do so by doing that cross multiplication. Now, in our first example, we ended up with a linear equation. What's going to happen here in our second example is we see we have a fraction equal to a fraction, but whenever I do this cross multiplication phase, I'm going to have 3 times x plus 2, which will be linear, but I'm going to result on the other side with x times 2x plus 4. Now keep in mind, it doesn't matter if I kind of put the 3 and x plus 2 on this side, or if I put the 3 and the x plus 2 on the other side. I usually base everything based off of my numerators. From here now, I'm going to go ahead and simplify. And what we see here is now that we have a quadratic, not only do we have a quadratic, but I have an x squared and an x term, I want to get everything on one side of the equation. So in order to do so, I'm going to subtract 3x to both sides and subtract 6. Now what I have to do is I have to see, all right, I have a quadratic such that I have an a value of 2, a c value of negative 6. I would like to factor this. And I'm envisioning factors of negative 12 that combine to give me positive 1, which I know are going to be 4. So this is going to be plus 2 to give me my 4, and this would be my minus 3. And again, we would double check, going back to our quadratics, here's a negative 3x, here's a positive 4x. Now from there, I would go ahead and I'm going to solve each independently using the zero product theorem. And I get x equals 3 halves, and I get x equals negative 2. And so what ends up happening here is now we can see that we end up with 2 solutions, because upon doing the cross multiplication, we had a situation where we end up having a quadratic. So our rational equations could sometimes end up with 1 solution, could sometimes end up with 2 solutions. We could even come into some that have more than 2 solutions. Something should be jumping out at you, though, as you look at the third example. And in the third example, all of a sudden we see that we have 2 rational expressions on one side equal to a fraction. So I'm actually going to use this as a bridge question for our first and for our second video explanation. But what I see in this case is, even though there's 2 fractions on the left side, they already have a common denominator. So if I wanted to, I could add these to get 3 over x equals 1/6. And now from here, I could solve this proportion. I would end up getting 18 equals x. Which again, is something that ends up being pretty basic for us, but what I want to do is I want to actually use this as a bridge, because there's another way I could solve this exact same problem. And that way that we're going to explain the secondary way is going to be the second strategy in the next video. So in the meantime, think about maybe what's another alternative strategy in which I could have used to solve that. And one of the hints is, what could I multiply everything by so that way there would be no more fractions? We'll talk more about